Good morning, everyone. I have to say I'm so excited. This is my first in-person conference in 2 years. I don't know about you, but yay. I know. And we're going to have an awesome time and great snacks and drinks and just getting back to the normal life. So good morning and thank you for joining us today at HAI's annual spring conference. The topic is key advances in artificial intelligence. It's so wonderful to see all of you here live, but it's also wonderful to know we have an online audience joining us worldwide. I really want to just give a special shout out to our online audience. You've been with us through so many events around the world in the past 2 years. We'll continue to include you in today's discussion and going on. So I'm Fei-Fei, co-director of the Stanford Institute for Human-Centered Artificial Intelligence, which we would like to call Stanford High. On behalf of my fellow co-director, Professor John H. Mundy, I'd like to welcome all of you to our conference today. 3 years ago, High was founded on a mission to advance AI research, education, policy, and practice to better human conditions. We believe that Stanford and academia in general plays a critical role in this mission. Since High's founding, we have only seen even more growth in AI technologies, businesses, as well as the debates, discussions, including concerns of AI's social impact growing. One of our most important goals for HAI is to become a platform that brings together technologists, humanists, social scientists, policymakers, business leaders, civil society leaders, and truly all of AI's multi-stakeholders to participate in honest discussions, debates, and intellectual discourse of this technology. This brings me to today, our annual spring conference since the founding of HAI in 2019. At this point, I'm delighted to be moderating this event together with my esteemed colleague, Professor Chris Manning, one of our associate directors here at High, as well as Professor of Computer Science at Stanford University. Chris, come on.
Thank you, Fei-Fei, and welcome everybody. As Fei-Fei said, today we'll be talking about key advances in AI. There are many topics that we might have covered, but we chose to focus on 3 main themes: accountable AI, foundation models, and embodied AI in the real and virtual worlds. Today we have an incredible lineup of speakers representing deep expertise from their respective fields and vantage points. We really appreciate them taking the time to join us today.
Our format today will be brief presentations from each speaker on their respective topics, followed by a panel discussion. We invite you to step to the microphones to ask questions, and you see they're positioned on the middle aisles. We'll also have the pleasure of hearing from Kavita Bala from Cornell, and we'll then wrap up the day with a fireside chat between Professor Kunli Alukutan and Bill Daly from NVIDIA, which will be a real treat.
To kick us off today, I'd like to welcome our first set of speakers to the stage who will be talking about accountable AI. Let's hope they're all ready to go. We wanted to focus on this topic today due to the increasing concerns about understanding AI decisions, maintaining data privacy, and fairness in AI models. These issues in part demand societal and regulatory solutions, and perhaps even new laws. But they are also a rich opportunity for technical AI advances in how you can produce interpretable AI systems, or systems that still work effectively on data that has been obscured to protect people's privacy. I look forward to hearing what our speakers have to say on this topic, as well as the questions from our audience. So please join me in welcoming Hema Lakkaraju, Dawn Song, Thakkar, and Liz OSullivan to the stage. You're meant to take any of the middle seats. Okay. We'll wait for you. Okay, great. Let's get started with our session. So for each of the 3 sessions today, we're going to have short talks from each speaker, and then we're going to have an extended time of panel discussion. So please join me in welcoming our first speaker today, Assistant Professor Hema Lakkaraju, a Stanford grad and now a professor at Harvard University. Welcome, Hema.
Thank you. Right. Thanks so much for being here, everyone. Very nice to see you all today. So today I'm going to be talking about a brief history of algorithmic recourse and, of course, some of the work that we are doing in this space. Before I get into the details, I would like to kind of start with a simple example to help us understand what exactly is algorithmic recourse, why should we care about it, and where this all started, right? So let's think of a simple scenario where we have a loan application or an applicant who is applying for a loan to a bank, and the bank is using a predictive model to determine if this person should get a loan or not, right? And in such a case, unfortunately for this particular applicant, the loan has been denied by the bank or the predictive model of the bank. Now, instead of just telling this person that that's the case, your loan denied and you're done, it would actually be helpful if we give more information to this applicant about why their loan was rejected or what can this applicant do in order to sort of improve their profile and then reapply for a loan. Right? So that is exactly what we are referring to as algorithmic recourse, a concept that became quite popular in 2017 thanks to GDPR guidelines, which basically outlined a recommendation of right to explanation for individuals who have been adversely impacted by algorithmic outcomes. Right? And basically, this kind of a recourse helps individuals who, as I just mentioned, are adversely impacted by algorithmic outcomes to find a path forward. Okay? And the moment sort of this problem came out in the open in 2017, there has been a lot of interest, and especially from the ML and computational communities, and people quickly realized that what might be useful as a recourse is a particular class of model explanations called counterfactual explanations, which basically say the following, which is what features of an instance should be changed and by how much in order to change a model prediction. Right? So, and people started using counterfactual explanations as a means for providing algorithmic recourse. In fact, these two became sort of so used together so kind of coherently and consistently that these two terms are now pretty much synonymous. So when people say algorithmic recourse, often they're referring to these kinds of counterfactual explanations. Okay. So now let's talk about the phase of 2017 to 2020, during which a lot of machine learning folks and other researchers in the community started proposing computational techniques for generating algorithmic recourse, right? Intuitively, a lot of these techniques use a very simple tactic, which is you take a point X, which has been negatively classified by a model, for example, like that loan applicant we just talked about, and then essentially add small additive changes to that point until it crosses the decision boundary to the positive side of the classifier. Right? So that's essentially the idea. And then once that happens, you return that counterfactual as a recourse. Okay? And of course, as you can see, the point X has several possible recourses. It can go in a different direction and go to C1 or CF1, or in another direction and go to CF2, right? And that's basically where most of the approaches differ, which is how to choose among several possible recourses, and also what kind of access to the model do the approaches need, whether they need just query access or gradient access or a lot more internal details of the model. right? So that's pretty much what a lot of approaches do. Okay, so now from the year 2021 to 2022, there has been a lot of critical re-examination of state-of-the-art approaches in algorithmic recourse. In fact, recently we ourselves have been conducting a bunch of studies to really understand the utility of algorithmic recourse and using counterfactual explanations for it, right? We carried out a survey with about 182 customers who have applied for bank loans in the past year, and we basically asked these applicants about the utility and helpfulness of counterfactual explanations prescribed as recourses. Okay? And the answers were very interesting. I'll show a couple of insights here which are relevant for our discussion. The first one is an overwhelming majority of the participants essentially said that this kind of a recourse is extremely useful for them. So that's good news. But we also found something which can be a very impactful finding. An overwhelming majority of the participants said that they would be very unhappy with the bank if the bank provides them a recourse, and then if they implement it and go back, they somehow don't get a loan. In fact, the impact of this is so huge that 83% of the participants actually said that they'll never ever do business with the bank again. Right? So clearly, this is a very important piece. So if at all we provide a recourse to somebody, we better make sure that it is really correct and we are going to sort of hold out that promise, right? So this observation in particular triggered a bunch of research in my group, and we started thinking about when can a recourse that we provide not be valid or not be useful anymore or not result in a positive outcome, right? And with no fault of the bank or the individual, there are algorithmic issues that come up which could cause this. For example, recourse generated by existing methods is typically not valid when the underlying model changes. Whereas in real world, models are regularly updated for a variety of reasons, including handling data set shifts and kind of consequent retraining, right? So now what do we do about this? What is our solution? So in order to address this problem, we thought about two key questions that underlie this. One is, how do we even characterize model shifts? And the other is, once we characterize model shifts, how do we generate recourses that are robust to different kinds of model shifts, right? And while there are several ways to answer these questions, the way we thought about model shifts was as if you take a model and its parameters, you can think of additive changes to those parameters as shifts of the model, right? Of course, alternatives can be used with our framework. And once we have this notion of a model shift, how do we generate recourses that are robust to this kind of shifts? That's where we sort of use a typical min-max formulation, like for those who are familiar with adversarial machine learning. The idea is to find a recourse that minimizes the worst case loss across various possible model parameters, right? And that's what we do. Okay, so we leverage these tricks from adversarial machine learning and adversarial training. And results show that this kind of a method improves the robustness to model shifts of recourses by about 74%. Okay? And in recent years, there has been more critical examination of state-of-the-art and algorithmic recourse. For example, thinking more about adversarial manipulation of this. How are adversaries likely to manipulate or game models or recourse algorithms in order to sort of induce undesirable biases or unfairness? And also thinking more about privacy risks of algorithmic recourse. Right? So if I give you a recourse, then I'm exposing some information about the model to you. How can an adversary use it in a bad way? Okay? All right. So with this, I'm going to thank you all for your time and look forward to more discussion about this. Thank you.
Thanks a lot, Hema. And now I'd like to introduce our next speaker, Professor Dawn Song from the University of California at Berkeley.
Great. Thanks, everyone, for being here. My name is Dawn Song, a professor in computer science at UC Berkeley, and also the founder at Oasis Labs. Today, I'll talk about towards building a responsible data economy for responsible AI. As AI and deep learning has been making huge progress, it's important to ensure that we develop responsible AI. And it's great to see that this is the focus of the first session today. There are many different aspects of responsible AI. For example, my group has been doing a lot of work in the area of understanding and improving the security and robustness of AI and deep learning systems. For example, here is example of some of our work on exhibits at the Science Museum in London. Given the interest of time, today I will focus on another really important aspect of responsible AI as well, related to privacy issues and beyond. As we all know, data is a key driver for AI and machine learning. And more data is being collected every day, and the size of the data economy has been growing exponentially. However, a lot of this data is sensitive, and handling the sensitive data has posed unprecedented challenges for both individuals and businesses. Individuals have lost control of how their data is being used. A lot of users' data has been sold without the user's awareness and the consent. And businesses continue to suffer from really large-scale data breaches. In many of these attacks, attackers steal sensitive information of hundreds of millions of users in a single attack. And most importantly, a lot of this valuable data is sitting in data silos and not being utilized due to privacy concerns. And we cannot continue the status quo. As we move forward in the digital age, these issues will only become more and more severe. And to the extent they will hinder societal progress and even undermine human value and fundamental rights. And hence, there's an urgent need for developing a framework for a responsible data economy. What do I mean by a responsible data economy, and what are the goals and principles? So first, we need to establish and enforce data rights. These data rights serve as a foundation of the data economy and prevent misuse or abuse of data. And also, it's important to ensure fair distribution of value created from data, so that users should be able to get sufficient benefits from their data. And most importantly, we need to ensure efficient data use to maximize social welfare and economic efficiency. And there are many challenges for developing a framework for a responsible data economy. There is natural tension between utility and privacy. And data is different from physical objects. Data is non-rival. And hence, we cannot simply copy the concepts and frameworks used in the analog world. And to develop a framework for a responsible data economy, it requires a combination of technical and non-technical solutions. Here, I will briefly talk about the three components, including the technical solutions, incentive models, and legal frameworks. So first, let's look at the technical solutions. It's not advancing. Okay, so first, traditional solutions are insufficient to protect data use. Traditional technical solutions focuses on data encryption that only protects data in transit or at rest. And also, data is either not used, or if it's used, usually they are copied. And once the data is copied, it's very difficult to control the further use of copied data. And also, the traditional method often relies on anonymization, and anonymizing data, as volume of research has shown, that is insufficient to protect users' data privacy. So we need a new technical solution that can provide data protection in use. And in particular, there are two needed aspects for this. One is that we need to be able to ensure controlled use of data without actually copying the raw data. And secondly, we need to be able to protect the computation output from leaking sensitive information about the input. So first, let me just briefly motivate why we need to care about protecting the computation output from leaking sensitive information about the input. Oftentimes, because these outputs are computed from the sensitive information from the input. Here, let's look at a concrete example. So we all know neural networks have very high capacity. So there's a question, whether these neural networks actually remember training data. And if they do, whether attackers can exploit this vulnerability to actually extract the secrets that were in the original training data from just simply querying the learned models without even knowing the details of the models, such as the parameters and architectures of the models. So this is what we set out to do in collaboration with other collaborators, including researchers from Google and so on. So in this case, we looked at the language model. So with the language model, we trained the model from a data corpus. And the goal is that when given a sequence of words or characters, the model will predict the next word or the next character. So in this example case study, we performed the following learning task, where we trained the language model on the email dataset called an unrun email dataset. And this dataset naturally contained users' credit card and social security numbers. Our work showed that by designing new attacks, the attacker can actually, by just querying the learned language model without learning the details of the model parameters and architectures and so on, is able to automatically extract the original social security numbers and credit card numbers embedded in the original training data. As an example illustrating that even as we train machine learning models, it's important to ensure with the protection of users' data privacy. And so this is an example of, on the particular learning task of a relatively smaller model. We also extended our work to show that even on really large state-of-the-art large language models, such phenomena also exist. For example, by studying GPT-2. And our work showed that by designing new attacks, a similar phenomena also occurs. Attackers can also automatically extract sensitive information, in this case, for example, personally identifiable information from the original training data. And so all this illustrates that even as we train machine learning models, it's really important to take the measures and precaution to protect users' privacy. So what can we do in this case? So in this particular case, we show that there are some mechanism that we can use. In particular, instead of training a vanilla language model, instead, if we train a differentially private language model, then this can significantly enhance the privacy protection for users' data, and also at the same time still be able to maintain similar utility for the model. And the next speaker actually will talk in more detail about what differential privacy is and how to develop some of these differentially private machine learning algorithms. So differential privacy is essentially a foundational privacy notion with formal guarantees. And volume of research has been done in differential privacy. But however, it's actually been very challenging deploying differential privacy in the real world for a number of reasons. A lot of data analysts and machine learning practitioners are not experts in differential privacy. And there are actually many different types of differential privacy mechanisms that one need to use depending on the particular analytics or learning tasks. So in our recent work, we developed automatic methods to make differential privacy much easier to deploy and be used in practice. For example, in our work in Chorus, we automatically develop program rewriting techniques and tools to automatically rewrite data analytics queries to embed differential privacy mechanisms into the queries itself, such that even though the analyst doesn't know anything about differential privacy, we can automatically convert a data analytics query into a differentially private query. And when the query is run on the database, it will also automatically return a differentially private query results. We also extended the work to develop new, essentially high-order type systems to be able to automatically analyze machine learning algorithms to automatically prove that it is differentially private. And our automatically derived bounds, in certain cases, have exceeded manually derived privacy bounds. and the work has won the Distinguished Paper Award. And also in our most recent work, we developed the system called PrivGuard, which is the first work that automates the tasks for ensuring that a data analytics or machine learning algorithm program satisfies the privacy regulation as compliant to privacy regulation, including, for example, GDPR and CCPA and so on. With this work, we enable users and data owners to specify their desired privacy policy, and by using static analysis of Python programs for these data analytics and machine learning algorithms, the static analyzer is able to automatically check whether the program is compliant with the desired privacy policy. And some of our work has been piloted in various industries, including Uber, BMW, and other sectors. So far, I've only talked about one of the component technology on differential privacy to enable responsible data use. So in fact, there are a number of different components that are needed to ensure responsible data use, and I call them responsible data technologies. So differential privacy helps protect the computation output from leaking sensitive information about the input. We also need to ensure that the computation process itself doesn't leak sensitive information, in particular, enabling us to do computation over encrypted data. And this is what secure computing technologies enables. And there are different types of secure computing technologies, including cryptographic-based methods, such as fully homomorphic encryption, secure multi-party computation, and so on, as well as using secure hardware, such as Intel SGX and secure enclaves and so on. And also, federated learning is another type of approach where allowing the data to stay on user's device and perform distributed machine learning across different devices to train the model. And again, the next speaker will will share more details in this area as well. And finally, distributed ledger provides a solution to ensure that users' data rights are kept in this immutable ledger and help enforce users' data rights. Okay. Oh, so to put this all together, by combining secure computing and blockchain immutable ledger solutions, we can enable a new type of data asset, a new type of assets that we call data assets to ensure that the user's data rights are maintained, and at the same time, data can be utilized in a privacy-preserving way. So I won't have time to finish the other components of this framework for building a responsible data economy. So overall, by utilizing these responsible data technologies, and also we developed new methods on data valuation using Shapley value and so on. So this can enable a new framework of a responsible data economy. Thank you.
Great. Thank you, Dawn. Next up, we have Thakkar, a senior research scientist at Google. Welcome.
Good morning, everyone. So today I will focus on how to train production machine learning models in the framework of federated learning with formal differential privacy guarantees. So the previous speaker focused on a few keywords here, and I'll go into more details. So let's start by briefly understanding what do we mean by the notion of differential privacy. So imagine we have a data set D that contains data from several users, and we use this data as an input to an algorithm, here denoted by A, to get out a model theta. So this algorithm is randomized, and as a result, there is a distribution that the algorithm can have over this data input. So what I'm showing is a distribution over some set of outcomes. Now imagine another data set D prime where I remove the user of, the data of one user. So in yellow, this is the new data set. And if I input this instead to the technique, I could obtain a different distribution over the outcome space. What differential privacy guarantees is that the change in between these two distributions, where the input was D versus D prime, would not change by much. In particular, it provides a mathematical guarantee for how much these two distributions can vary for any particular set of outcomes. So no matter what the input data set was among these two neighboring data sets, it will be difficult for an adversary to distinguish looking at the outcomes. So with this notion, in 2018, researchers from Google came out with a technique called differentially private federated averaging. This is a technique to collaboratively train a machine learning model using distributed mobile devices in the setup of federated learning. So here's the setup. We have a population of mobile devices. They want to train a model. The technique proceeds as follows. First, we uniformly sample a subset of devices. Each of them gets the current model, and then they do some tasks at their end. They use their local data to compute what is called a model update. There is an operation called clipping. So they clip their update and then send them to an orchestrating server. So this average update now needs to be privatized. So some calibrated noise is added to this update, and this is how we obtain a differentially private update. The noise can be added by the devices or the server, but basically it needs to be calibrated such that it hides the influence of individual devices. Now, once we have this differentially private update, it's fed into the model, and this training proceeds. So this is how iteratively you can train a model in federated learning such that it can have guarantees of differential privacy. In 2020, what we did was we trained a 1.3 million parameter language model using this technique. This was used for next word prediction for Spanish language users in the Gboard app. To give you an idea of how intensive it was, we trained for 2,000 rounds. It took around 3 weeks to complete, and 20,000 devices participated per round. In terms of utility, we saw model quality as well as utility improved over the baseline that we had. So for example, these metrics, we saw positive improvements over the baseline. We also provided some empirically tested privacy advantages over non-DP models for this release. So for example, something Don talked about earlier, we evaluated for unintended memorization of data on this model. However, for a differential privacy guarantee, what we could say was if we can ensure uniform sampling from a known population size, then we can guarantee then we can provide a differential privacy guarantee as follows. So the important point here is that uniform sampling is required for what is called privacy amplification by sampling to provide a strong privacy guarantee for this technique. And we actually show that this is infeasible to provide in practical training. To go into a bit more detail, why is it so? There are various challenges that we encounter in actual real-world training. For example, a device can have a limited availability. It may not be available for the full 3 weeks that we train over. It could be, for example, not charging, not connected to the internet, not idle. So there are various reasons where it could disconnect and reconnect in training. For efficiency reasons, communications are started by devices. So the server doesn't ping all of the devices that, hey, are you available? It's the other way around. So they are client initiated. In particular, at any point, it's difficult for even the server to know what is the size of an active population. This is also incompatible with load balancing techniques. So to summarize, we had a protocol later that was feasible, but it required some complex changes, and it still relied on amplification with a large number of devices being available. So in 2021, we came up with this new technique called differentially private follow the regularized leader. I'll briefly go over how it operates. So we have the same setup. The model is now sent to a batch of devices. Each device does the same that they did before. They compute clipped updates. To the averaged update, the server does something different. It uses a tree aggregation method. I'll not go into details in the interest of time, but this aggregated update is used to have a model for the next round. What's important is there is no sampling requirement for this technique. So the server can just operate on the next batch of devices that is available. And in the paper, we also show that it performs, this technique outperforms federated averaging without any amplification, and it is competitive with DP federated averaging with amplification at various settings. So with DP-FTRL, what we did was we trained the same 1.3 million parameter Spanish Gboard model. This training ran over 6 days, and 6,500 devices participated in each round. So it's a 3x gain in both training time and devices. We had to make several other improvements. For example, each device could participate at most once daily. We tightened the privacy accounting. But with this, what we were able to do is to train the first production neural network that trained on user data and was announced with a formal differential privacy guarantee. So what was the, and this was announced in February this year. What was the guarantee? So we were able to satisfy a user level ZCDP guarantee. It's an analog to differential privacy. You can also get differential privacy guarantees for this from this guarantee. And we also observed model quality improvements over the previous DP federated averaging model. In terms of future directions, we are currently conducting research for better aggregation mechanisms for prefix sums, which is used in this FTRL technique. And another direction is to train more production models that have formal differential privacy guarantees for them. So this work was the result of the efforts of people from multiple teams over multiple years. So I'd like to thank every one of them, without whom this work wouldn't have been possible. With that, I'd like to conclude. Thank you.
Thank you, Om. Now I'd like to welcome the last speaker for this session, Liz OSullivan, CEO of Parity.
Hi, everyone. My name is Liz OSullivan, and unlike these amazing colleagues here on the stage today, I am not a lawyer or a data scientist or an academic of any kind, but instead I'm a serial startup masochist, as I like to say, and an activist, which means I'm really good at making pitch decks and yelling at politicians in the hope of enacting meaningful change. Oh, thank you. Wasn't expecting that. But what I am is somebody who has seen the way that things work practically in industry, where a lot of these concepts and these technologies are made and put to use. And for the last 3 years, my focus has been on the responsible AI marketplace, which means that I've generated quite a lot of knowledge about the way that large enterprises and corporations are tackling these questions of how to make their AI responsible and fair without discriminating against or harming certain minority populations. And so if I talk about the responsible AI marketplace a little bit, 3 years ago when I started on this journey, we began with doing a lot of education. And so people really came to us, and every client had their own line, and this client line was usually something like, oh, our models aren't biased, we don't use age or race or gender as inputs to our model. And then they learned a little bit more, and so a couple years later it became, oh, our models aren't biased, we don't use zip code because we don't use proxy features, and so on and so forth. And so today, the rest of this talk is going to be a couple of the more common misconceptions that I think we keep hearing more regularly today, and some unanswered questions that I think it's really exciting to see progress, especially even just in the talks that we've reviewed this morning, but questions that we'll be working on together as the combined research and industry communities. And so the first misconception that we hear quite a lot is that, believe it or not, a lot of large enterprise believe that they have reached consensus on how to debias very particular forms of existing enterprise AI. And this is particularly heightened when we look at tabular data and different kinds of models with regard to trying to comply with existing laws, in particular anti-discrimination laws. And so, of course, I'm talking about this notion of disparate impact, which is the unintentional discrimination against protected classes. It's a concept that's created by people, that's used mostly in the legal system, but it is also the name of several metrics that purport to measure this kind of an unintentional discrimination. And people tend to think that once you have measured this, then your work is done. As long as you don't cross a certain threshold of performance between protected classes and the majority group, then your AI is compliant, it's not discriminatory. And so in order to get to this threshold, which I think is very much under debate, people use a combination of pre or post-processing techniques, but what they neglect to understand is that sometimes these techniques in particular industries can actually themselves be illegal in the application of it. And industries disagree with one another, and they actually can introduce new risks or political risks with the treatment of different protected groups as differing from one another. And then if we think about language models, there's so much to talk about here. I'll actually come back around to this a little bit later on today. And so for the last few years, we in the activist community have been yelling very loudly about the need for regulation. And I think a lot of people think that once we do get these new laws, many of which are actually proposed already, that everything will be okay. And that no one will get harmed by either intentionally or unintentionally by these algorithms. And I can tell you that that's just simply not true. In fact, we saw the country's first AI-specific regulation in New York City earlier this year, the Automated Employment Decision Tools Regulation, which reaffirms candidates' rights not to be unintentionally discriminated against by virtue of the, again, notion of disparate impact. But the law only calls out 3 categories that people have a right to not be discriminated against based on their age, their race, or their gender. And as we all know, there are many other minority categories that would otherwise be implied in the existing laws. And so in some ways, by calling out these 3 protected categories exclusively with regard to AI, the lawmakers in New York City, the City Council, actually made a huge oversight in omitting people, for instance, who have disabilities. Now, that would potentially give cover to large enterprises who may otherwise try to measure the effect of these kinds of algorithms on disability communities, even though it's very difficult to get access to that demographic data. And so in some ways, this law may have actually made things worse. And of course, we're all looking forward to the EU regulation, which is probably going to be agreed upon this year, the AI Act. And the AI Act, in a lot of ways, is very similar to the General Data Protection Regulation, or the GDPR. And I think that it's really important to note that billions of dollars in industry have been spent trying to comply with the GDPR because of this really significant fear that there would be massive penalties, on the order of millions of dollars, or a large percentage of the revenue of the company. And so this has been many years now that these companies have spent all this money and time and effort to comply with the law, and the enforcement simply has not shown up. And so there's really a big concern that this will continue and will have actually discouraged people from trying to comply with the AI law from the EU when it actually does arrive. And so I think it's important for us to try to examine whether the correct incentive structures actually do exist in industry as opposed to potentially in academia. Don't get me wrong, I'm a startup CEO. I believe in industry, and I do know that we have been doing quite a lot of really good work in this space. But I think it's important also to recognize that the startup incentives are sometimes out of line with what we want to create with regard to responsibility in the world, or accountability for our algorithmic systems. The venture capital market creates really interesting incentives for hypergrowth. And I'm not thinking, of course, of my colleagues at Parity here, but I am thinking about the very clear pipeline for especially heightened awareness of computer vision companies that have transitioned from really good social goods type work into the military industrial complex, the prison industrial complex. And so I think one thing that we do hear a lot at Parity is that there are companies who really just want a simple solution. They want to sort of hide behind our brand, our logo, and try to ethics wash, as we refer to it, with a simple solution that may not actually go all that far. And it's very easy for us to say no to these engagements, but when we do, there are competitors in this marketplace that are very happy to take on these ethical quandaries and dilemmas. And so I do want to say there are plenty of wholesome actors in this space, and so really rooting for them and cheering them on. And so it'll be very interesting for us to all check back and see how we did in 10 years. And I think the most important question, which I'll spend probably maybe a little bit too much time on here, but just another minute or two, is this question of how can we sufficiently manage risks on models that have impossibly large complexity? And in particular here, I'm referring to computer vision models or large language models, where the notion of debiasing something is really an infinite task. And so how do we even define bias in language? I don't think that we have consensus on this at all, because isn't all language biased? And when it comes to large language models, there's a really important debate raging that I don't think is getting nearly enough attention at all. And this is this notion of curating data sets and training data, which is sometimes referred to as censorship, which I find very odd. Because the notion of redacting training data for toxicity is referred to negatively as potentially violating some form of freedom of speech, And because it's very often that the organizations who make these arguments are those that are also saying things like that partially conscious AI may already exist to some degree. And I'm not here to comment on that, or whether it's possible now or whether it ever will be possible. But if you will forgive me the really bad joke, I will say that on this question, I do find myself to be very personally biased in favor of curation because of my experience using no-code tools to train computer vision algorithms. And when we did this, math alone was never sufficient to, for instance, teach the algorithm that not all wedding dresses are white, and some cultures use red to express that, to celebrate that occasion. It actually required human experience and a diverse team who was actively testing for this because they knew already that it existed. And curating data was the only way to sort of train and teach these algorithms that other cultures exist. And the sensitivity is most heightened, I believe, around the debate of how to debias large language models. And again, I'd like to say to the organizations who are claiming that perhaps these models are somewhat conscious, or that training data redaction may actually, in virtue of protecting certain people, violate some notion of free speech, that this is potentially, interpreted as, we can call it being a bad parent, right? Because what parent would, for the sake of some free speech ideals, sit their child in front of Reddit and ask them to consume quite a lot of toxic content that they would then learn about the world from that information, or potentially even memorize it? Because if we are going to create a consciousness, and again, not commenting on that today, then we are going to be the ones who teach it our concepts of morality and ethics, and we can't just rely on this emerging from nowhere, because it simply won't. But there is good news, and I do think that it's really, really heartening to see. It's heartening to see that this field that we are working in is extremely popular, and it's growing in popularity every day. Actually, at Parity, our very first intern was a high school senior who's now at Berkeley, and she told me that she knew that responsible AI and algorithmic fairness was something that she really wanted to pursue with her career already. And in many cases, the right people are at the helm. I can think of dozens of examples of incredible people who are running organizational groups at universities, independent research organizations, and even in large tech companies against impossible odds. And again, as an activist, I can say that it's been really amazing to see how quickly regulation has progressed in this space. So help is on the way, and it does seem that it's been really a fight that has garnered a lot of attention and a lot of progress. So it'll be very exciting to see how things progress over the next couple of years. Thank you.
Thank you, Liz, and thank you to everyone on our amazing panel. A lot of interesting topics there, ranging from algorithmic recourse to how we can do learning with privacy, and then talking about how some of these issues of regulation and addressing bias do or don't work out in the real world. We're hoping now to have half an hour of discussion, and we welcome the audience to come and take part in the discussion. So if you have a question that you'd like to ask, please come to one of the two microphones. There's one there and there's one there. And if you could just very briefly introduce yourself before asking the question, that'd be really helpful as well. But let me start off with asking one question, and I guess I'm going to key off Hima's first talk, but other people could have opinions. So, I mean, overall in this session, we heard, some good news, that there are new ideas of giving explanations for algorithmic recourse, new ways of learning with differential privacy. And I think that is actually good to say, because there is real good news, right? That really for almost the entire history of machine learning, people ignored all these issues, and now that there's a lot of focus on them, it is actually leading to, robust new areas of study and genuine algorithmic advances and letting us do things. But I was still left a bit questioning as to this algorithmic recourse. So the idea is you're going to tell people what would take them over the line to make them eligible for something. And I was sort of sitting there thinking about something like an insurance scenario, and I was wondering, how do they, so there are different ways you could move in different directions, and Hima mentioned that problem, but no matter which direction you move, isn't the answer for how you'd be able to get insurance with us is, if you lived over in the next suburb, then we'd give you insurance, or if you owned a more expensive car, then we'd give you insurance. I was, in the abstract that you had 93% of users said they'd be happy to get recourse and be useful, but would they really be happy when they were told the answer? I was really left wondering about that question.
Right. No, I think that's a great question. And while we didn't have time today to go into all the mechanics of how to think about recourse so that we don't run into these kinds of problems, right? Like I think sort of one of the things is over 3-4 years, different methods have been proposed. And some of the methods, especially the newer ones, especially try to avoid scenarios like what Chris mentioned, which is we might not want to tell people to act upon certain features that are not actionable, right? And domain experts can provide us with inputs on those features, whether it is telling somebody that, go live in another suburb, or whether it is telling somebody that, get a master's degree, but also without increasing your age, right? So people have sort of thought about these kinds of things, and this is where thinking about like causal graphs or structural causal models when recommending recourses can be like a very useful sort of an approach to address some of these challenges, and that's something that has been proposed by prior literature. Of course, it brings up new challenges like, do we really have causal graphs of real world data sets? Maybe not, but then again, we have some answers in the sense that, we can use some of these variational autoencoders and so on to kind of create latent spaces, capture some of these relationships, learn them from the data, and then sort of use it so that we recommend recourses that don't sound outlandish, right? So that is one of the ways in which we can address this problem. Of course, that said, the thing that while I'm cautiously optimistic about like where we are going, I broadly agree with your point that, there could be several unknown unknowns there. And we are sort of, I think machine learning as a field, there is a tradition to progress, we find an area, we sort of propose a bunch of algorithms, then realize the pitfalls of those, then take corrective measures and rethink, right? That's why I was saying, like, we critically re-examine and then redo things. So yeah, that's what I would say to that.
Does anyone else want to make a comment on that, or should I grab the next question? Oh, okay, well, I'll take the first audience question.
I think a gentleman was
Oh,
first.
okay, sure.
I'm Ted Selker, and I've thought about AI and user interface most of my career. I'm thinking about this box. We got this box where we got the computer and the AI doing stuff, and then we have the person. We have a system with people. And there's a couple of ways that I kind of want you to maybe answer about that. One is that I've worked in voting technology where a lot of the beliefs of people about how secure things are trumps what actually is. And it's very hard to see what algorithms have done, whether they're really doing what they say they're doing, relative to securing things. So that's one place. The other place, very quickly, is just you take a look at this Romanian that hacked all sorts of famous people by just kind of guessing passwords and their, whatever. So and the question is, a lot of my more recent papers are about how to make people recognize how to make themselves be more secure, how to make privacy happen at the interface between the person and the system. And I just wonder if either of you guys have any comments on those things.
Someone game to address that?
Maybe could you clarify the question a little bit more? Like, right, so you're asking about security and privacy. So maybe you can clarify the question a little bit
Well,
more?
basically, people are often losing all of their privacy and anonymity and all of the things that we're trying to support right at the moment when they are interacting with the system. And we don't necessarily help them know when they're doing that, but also we don't give them good tools for seeing whether they're doing that. And then also within the system, people have no idea whether they're doing all these fancy things that we've written all these papers about how we're anonymizing and protecting people's privacy. And so what are we doing, what are you guys thinking about relative to how we make people understand what they're doing that makes this accountability happen?
Okay. Yeah, sure. Yeah. Happy to help. Yes, I think this is a really great question. Also, it's actually a huge challenge that the whole security and privacy field is facing. In the sense that, yes, like you said, we are developing all these technologies and also helping the actual engineers to, when they build a system, to make it easier for them to build more secure and privacy-preserving systems by developing all these tools. And also on the user side, however, users are not as sophisticated. So there are a couple of issues. One is, right, unlike a system, you can see how fast it is. So it's very easy for users to tell whether the system is efficient, is well-performing. But in terms of security and privacy, it's very hard for a user to tell apart. And even it's very hard for actual experts from just looking at the black box to tell whether the
Maybe
system
impossible.
is secure. Right, exactly. So, and hence, this actually has been an issue for example, for companies. One company spends a lot of effort improving the security and privacy of the system, and the other one only just claims that it has good security and privacy measures and not actually spending the resources. So you can see one actually use a lot of resources, but for the other one, they can use the resource to do other things to improve the business and so on. So from the user side, because the user cannot tell, and often the companies who actually don't spend the resources, actually they are not necessarily at a disadvantage on the market. So this actually has been essentially a discouragement for a lot of companies to put in more resources in the space. But however, of course, with regulations like GDPR and CCPA and so on, so this has put more requirements on the company side to put more resources to address these issues. We also recently have actually done a meta study in the effectiveness of, for example, data rights in GDPR. And what we have seen is that one, yes, it's actually very hard for users to even know all these different data rights, and it's very difficult for users to, in practice, to actually try to enforce these data rights as well. So overall, I would say it is a big challenge, and that's why for the whole field, I think we need to essentially combine the different aspects, including, as I mentioned, technology the legal aspects, and also some the proper incentive models to
Are there any other thoughts?
Right, exactly.
Yeah, I just wanted to quickly chime in, and I think I agree with a lot of the points that Professor Don made. And I think it's kind of like there are multiple parts to this problem that you discussed, and it's obviously a very deep problem. So one is, I think Don mentioned a little bit about the regulation. While we may not entirely know the full sort of the pipeline of, okay, my data has been taken, it's going into this recommender algorithm, that algorithm, something else, and so on. Ideally, if we had that level of understanding and transparency, that would be great. But given that, that is almost like a sort of an impossible pipe dream, maybe even like thinking about regulations in the form of, while each individual may not be able to see this entire chain, kind of giving some high-level guarantees in terms of, yeah, this company is adhering to these standards, could be like one first step to that problem that you're worried about, which is what is happening to my data, how do I sort of think about it, and hopefully my data is still private and so on. So I also echo that sentiment that maybe regulation can help a bit, but I think going forward it might be interesting to also explore when used to see how to train people to be more aware of these kinds of things as end consumers, right? So that is, yeah.
Okay, maybe we should go to a next question.
Well, good morning. My name is Misha Dollar. I was academic professor at King's College London for many years. I'm now chief architect here in Ericsson Inc. In my community, the wireless community, we really tick around standards. They have been very powerful in bringing together a very heterogeneous ecosystem, everybody with their own commercial interests. And as part of the standardization processes, we also dealt with a lot of security issues, with a lot of privacy issues. So my question to you is very simple. Do you think it's time now to start talking about global standards, maybe one standard of AI, which would help with security, privacy, and also maybe also with the federated AI learning issues, interoperability between models. So I'd like to get your view on that. Thank you.
Yeah, I can talk about that a little bit. So, we pay pretty close attention to this because I think that one of the counter arguments against regulation has been historically from large industries who really don't want it to come, and their proposition is usually something along the lines of, oh, we'll just follow certain standards. And usually this is the first step towards getting a regulation anyway, and so it's been really heartening to see, here in the United States, we have NIST is just in the process of putting out their anti-bias framework, their risk management framework, and the White House is working on a digital Bill of Rights, which is, a form of self-regulation as well. But other countries are way farther along in this process, so including China, Singapore, Japan, lots of companies have, not companies, this is where my life is, but countries have been working really hard to create their own standards. And a lot of them, there is a lot of overlap, right? Like data protection, privacy, there's, right to explanation has made a resurgence in some of these standards and things. But I think you would have a really big challenge in trying to get all of these different value systems to agree in certain areas, like these corner cases. So I do think that there's value in trying to create a global standard. I think that if there were a place that it might happen, in the United Nations. But I think it would be pretty difficult to get people to agree uniformly across different populations, just because of the differences.
It's a good point. I'm sorry to interrupt. What I meant is not a legislative kind of standard. I mean actually really engineering standards, right? So we have succeeded really, apart from the regulatory frameworks, which give the envelope, to actually give technical standards, which would help then, I think, also with a lot of the privacy issues. That's what I meant. Sorry,
Yeah.
Just wanted to clarify that.
Do you have any thoughts on whether there could be shared federated learning? That's a corporate challenge as well as technical challenge.
Right, so what I'd like to say is having a uniform standard for all kinds of applications might be difficult to have a benchmark that this is what needs to be achieved. Like from situation to situation, it can be different, and what privacy means. what leakage implies. And so, for example, for our cases, even if you show that models don't memorize data, that can be a huge step forward in showcasing how the protection might work. Of course, providing strong guarantees against leakages are even further steps, but then what guarantees do you get can differ from one scenario to the other. How strong the guarantees are, what data is being protected. So yeah, it kind of depends on what application you operate in. Yeah, research is taking steps towards showcasing different kinds of protection via various methods.
Any other thoughts? Go on.
Yes, I think in these different sub-technical areas, there are standards consortium where different companies and academics are coming together to make progress in the space. So for example, in secure computing, there's a confidential computing consortium where Google, Microsoft, Intel, a lot of the top tech companies are part of this global consortium that's actually setting up standards and unified APIs and so on to enable secure computing.
Okay. Thank you.
Yeah. Okay, so moving on, I didn't actually realize there was a third mic up back there, but we've got a person at it, so I could take that question.
Thank you so much. Great talk. Awesome talk. My question is for Liz. I think that a big problem in today's big tech is political censorship. Google, co-founder of this conference, has been clearly accused of political censorship on both sides, left and right. Either it's the search engine, either it's YouTube. I wonder whether what Elon Musk tried to do last week is the solution, is essentially having people with a different political point of view in the board of directors of these companies, because I don't believe in regulation. So if you give politicians the power to regulate these companies, you're going to get the bias of this or the bureaucrats of whoever embedded in those regulations. So I still believe that the free market is the way to go, but I don't know what the solution is. Thank you.
Yeah, so I do think that when we talk about political risk, there are a number of ways to interpret that, and certainly what you're talking about does exist, and it does happen. Like, there's no question that email providers, the research that just came out the other day, that they filter, and it all comes down to user data, right? Like who's marking what as spam and who hangs out in that email server. But when I was talking about political risk, I was actually mentioning something more along the lines of treating protected groups in a different way in order to try to balance outcomes across those protected groups, which may be fine under certain administration, and it may be actually pursued actively under a different administration. So I think political risks are a very unique kind of risk for organizations to try to defend against, because it does shift, right? The administrations change, right. And so that shifts pretty regularly. So whatever regulations do exist, I think we need to be very careful that they're adaptable and that they're flexible enough to incorporate new research as it becomes available.
Thank you.
I feel forced after that to ask the opposite question. So how many people saw John Oliver last night? Anybody see it? Not very many. So John Oliver last night was on data brokers. And basically what it was about was this enormous unregulated market of trading of all of our data. So that all sorts of apps you use regularly collect data, and the various companies can make money by selling it to other people, and then they sell it to other people, and they sell it to other people, and the people who it ends up with, actually it's sometimes the government, but it's often different companies, and sometimes it's political parties, so they can send you targeted ads. This is the free market at work, right? They don't pay too much attention. They don't encourage people paying too much attention to it. There's a lot of money by trading around everybody's data. Now, in all honesty, that's not an AI issue. This has nothing to do with AI. This is just raw data being shared around the system. But it doesn't really seem like the free market by itself solves that problem. In fact, it's the free market that is building this problem. So I wonder if any of you have any thoughts about that.
So that's exactly the data economy, responsible data economy problem that I was talking about. Exactly this market of selling data and without users' awareness and so on. And sometimes the data is sold under the premise of anonymization, but actually we all know that it actually doesn't really protect user privacy and so on. So, and that market overall even and the market about how to use the data, like you said, and sell to others and so on. This data economy is just growing like really fast and so on. So that's why you mentioned that the data economy is not an AI problem, but actually that's why in my talk, actually at the end, I wanted to make the point that building a responsible data economy is an important part of responsible AI. Because at the end of the day, when you are serving ads, when you are trying to train machine models to figure out who to serve the ads to, it is essentially you are training models using this data, which is violating users' privacy and so on. So it is a really important problem. Yeah. And so that's why we need all these different combination of solutions, in particular helping users to maintain better control of their data and their rights to data, and being able to get better benefit from the data.
I agree that AI is part of a customer of the data economy. Are there any other thoughts?
Yeah, I mean, I echo some of these sentiments, and I agree that I think free economy of the data is probably not going to solve this problem. I think it's potentially going to address some of the issues around incentives of obtaining data, but I think maybe this issue of like privacy or like data leakage, or like as you said, like people having their hands, different political parties maybe having their hands on the data of different people, which has been obtained through the free market, and using it for targeted ads, those problems remain, right? So even if you create a free economy, so that problem is not solved. It might be solving some of the other problems related to incentives.
Yeah. Okay. So we go on to the next question.
Hi, good morning. Carlos Oriol. I'm a student of Professor Song at UC Berkeley. I know we were listening in some of the questions about the regulation and the standardization of the algorithms themselves, but I'm looking more at the data itself under the assumption that if we have some ethical data in usage leading to the training of the model, then the AI itself will be ethical. And so is there currently a empirical measurement of how ethical a data set might be, how unbiased, and if so, how is that enforced and how is that regulated? Who is enforcing it? I'm thinking like a LEED certificate for buildings, but for data.
I know of a number of organizations that are providing consulting services on that regard to say, that I don't know that there's like an empirical metric of, how ethical a data set is, but it's one of those things where you kind of know it's not ethical when you see it, right? And there are so many examples of that in all these open source data sets that are, very clearly imbalanced, with regard to gender representation, or various kinds of marginalized communities not being present in the data sets. So I think it's a lot easier to see the effect rather than the data sets themselves, especially when you think about, this is the secret sauce. So big companies aren't going to publish necessarily metrics about their data set. But I do know that there are, small organizations and even the big 5 consultancies who are working really hard to qualitatively assess, some of the data sets to find out if there's anything obvious that jumps out. But it would be really interesting to try to standardize various measurements. It's not something I've seen yet.
And just a quick follow-up, when you look at the effects, it's obvious that there is some bias in place. Do you think at that point it's a little bit too late to then come back and try to fix the model itself? Should there be something in place beforehand?
Never too late, right? There's always the future. These algorithms are still in production making decisions. Even if they've made bad decisions in the past, they can make better ones in the future.
Thank you.
Okay, should we go to the question up the back?
Thank you. My name is Lu Yan Fang. I work as a Seattle startup healthcare called Prescriptive Health as a AI and the Data Chief AI and the Data Officer. Also, I want to mention the point, it's really Michel Dollar. He brought up the standardization. I started the effort called AI-HCCI. The intent is really how do we get to a place so we can test the methodology, we can measure the result, we can have a place to educate. Also, we can document how to use each AI solutions developed. So where I come from is I worked at IETF, the Internet Task Force, for about 18 years. That's how we get the internet running. There is a standard organization, not government run, it's engineering run. But you need to have a common agreement, every protocol, how to get interoperability, how to get consensus, and stamp into RFC. That's where I think at the point now, I can see a lot of companies come to say, we're number one, because this consulting company said we're number one, and we're number one, which is actually working, which is actually not working. If we have a place, can test them through and publicly publish the result without disclosing everybody's secret sauce, but the common data source used, how you manipulate can be your technology, but have the result and the document down how to use that, how the doctor can use that. If you use it wrong, then it just not serve the purpose. So that's something, I think it's time for the community to get together to have such an effort. It's not about government, it's not about total democracy, it's to have a common place to set the standard interoperability.
So the question is, can we achieve that? Is that roughly it?
I think it's an
Can we
advice.
achieve that if we make effort? It's going to be very hard because same as the internet, multiple parties, all different opinion, different agenda, but it's definitely achievable. I see some other countries already started such an effort. So if we can start within US and globally, eventually,
Does
start
anyone
from
have
small.
any thoughts on whether that's achievable or how?
Yeah, I just wanted to comment on that a little bit. I think, thank you for this comment. I think that's actually valuable advice. I think it's less of a question and, it's more of like guidance, which is really needed at this point, right? And I think, what she seems to be suggesting is also that let's not wait for the government to do something, all the big companies to come together and do something. Why not think of an academic consortium? And I think Professor Don has already given some examples of such for privacy. We can do that more broadly for other areas as well, so that we can lay out guidelines of, this is maybe how you want to use, like a doctor might want to use AI, and like here are the known issues, here is how we want to see the workflow going and so on. So I think, yeah, at least starting in the academic community might be a good first step. So thank you for that thought.
Thank you. And with the practitioner, like hospital doctors,
for sure.
right?
Yeah, thank you.
Does anyone else have a comment, or do I move on? Okay, wait, I think it's the person on this side next, thanks.
Hi, my name is Eddie Karot. I'm a retina surgeon here. So this might be a question for Himabindu with your work with high-risk data and applications. So doctors are pretty good at knowing when they don't know and asking for help, but models not necessarily. And it kind of actually baffles me how the FDA doesn't have a prerequisite for approval for like out-of-distribution detection, for example. How important do you think out-of-distribution detection is for high-risk models?
That's a great question. So yeah, I think it is definitely, if we are talking about out-of-distribution detection just generally as a problem when learning, let's say, medical models or like even detecting shifts that the data is undergoing as you run models on it. I think broadly the problems of data set shifts and thinking about how to detect them, monitor them, and also if needed sort of replace your models, I think those are very critical pieces. that are absolutely essential for healthcare. Like we collaborate with some of the hospitals in the Boston area, and that's one of the key things that they want to first focus on, right? So we can use all these models to help, let's say, a radiologist, to sort of like see or even do early detection of, for example, tumors. But we want to be able to see this when somehow there is a shift in the data, like whether it's caused by an external event, whether it's caused by some, diseases developing, like we saw in the past 2 years. That shift, detection of that shift, sort of like correcting it, and even like replacing models. I think that entire area is definitely very critical for high stakes things like in healthcare. Yeah.
And it's kind of crazy that the FDA doesn't require that. I mean, you have models that are diabetic retinopathy or not.
Yeah.
And if something else comes in or if there's a shift, they won't tell you.
Right. Yes, I think this kind of sort of monitoring, I guess that's the broader term that's sort of being used to refer to a lot of these detecting shifts, correcting for them, even checking if different groups are being treated well in terms of the model predictions and so on. I think more than like sort of even not just like sort of having some of these, as you said, the guidelines at the beginning stage, like, oh, when you deploy the model, this is what you should check for. We definitely need to have guidelines for monitoring stages through the life cycle of the models. 100% agree with you on that.
Maybe go to the person at the back. Hi.
Yeah. Hi. So this may be more of a philosophical question, but I'm not sure. Most likely this is for Liz, but others feel free to chime in. So I heard many of you talk about unintentional bias, and even though there's a sort of lack of clarity on that, my question today is more about intentional bias. What I do mean by that is the data in some cases that we get and as modelers choose to model is inherently biased because the data sources are biased. For example, in banks, when there are loan applications and some systems are deployed to automate that using ML. There is also a component of human-centered AI which seems to be missing in many of these applications that are intentionally biased. For example, before, if people's loan applications got rejected, they could still walk into the bank and have a chat with somebody and see what went wrong. How do you folks see addressing this problem when we move to fully automated pipelines, where people don't necessarily know the reasons why their loan got rejected, for example? And just to elucidate more, there are some marginalized groups by default whose loan applications are rejected. This is a known problem. And the explanation, the intuitive explanation for this is that, well, the stats do represent that the repayment in such marginalized groups is low. But moving from a sort of human interaction to ML-based interaction, as an end user, if I'm from a marginalized group, what do I expect to see differently? Does that mean just utilizing a sort of explainability laden AI approach, or does that mean human-centered AI approach, or something else?
Okay.
So just to add a thought.
Shall we get some answers now?
Yeah.
Liz, do you want to go first?
Sure, I'll be brief just to say that I think there's a lot in that question, and I do think that it is a very philosophical question in nature, and in some ways I can imagine an argument being crafted that says that failure to correct for historical bias is actually intentional discrimination, and I really like it. That's not something I've heard before. But just to say, maybe let's tackle the most important, or what I would maybe have pulled out as the most important thing is, like, are we ever going to get to a point where banked loans are completely automated decisions. I'm not sure, and I think that because there are laws that exist that require adverse action notices to be created for every application that comes in, that's a relatively recent law, and there are a bunch of different interpretations of it, but it does exist, and companies spend a lot of money trying to make sure that they can explain, at least in a bare minimum kind of way. So it's been really heartening to see some of the proposals for algorithmic laws have that same provision, and it's something I feel really strongly about too.
Got it. A short addendum to that would be, should we put some effort to model what we think is an ideal world, or is there some sort of framework, a guidance framework to even consider what would be the most ideal? In other words, should we model what exists, or should we model where we want to go to? That's the question.
I have a very strong preference there, but I bet we would all disagree, right? I think that it'd be pretty difficult from a corporate perspective to try to comply with the law to create a data set that's largely synthetic, representing something that is the world that we want to see. So I'm not sure. I don't know the answer.
Yeah, you probably should go on.
Hey, my name is Sid, and the question I have is related to algorithmic recourse in the landscapes of marketplaces that move very, very quickly. Think like advertising, where if you change the creative, that's information you're telling them and it gets better. Or if you're an Uber driver, telling to drive here, and that you'll make sure you get paid more. How do we think of the recourse information affecting the market dynamics, especially places where it's really quick? And how do you approach those landscapes? Because more and more things are becoming like marketplaces.
Yeah, no, that's a very, very great question. So I think currently I feel like if you're asking about are we ready to do that, right? So with existing approaches and so on, I would be a little bit cautious because I think this is a fairly, as I was discussing, it's a fairly new field, and I think there are still people are kind of figuring out that here are the pitfalls, here are the pitfalls, and here is how we should sort of think about fixing them and so on. But I think as we sort of go forward, I definitely was also recently talking to one of my colleagues about this exact situation where, so far we are thinking of recourse in terms of there is a big entity, they're sort of giving like a point-to-point recourse, right? So the bank says something or the insurance company says something. That's the kind of settings we are trying to design algorithms for, which makes sense, that's like the first step. But I think going forward, as you said, if we were to kind of scale this to marketplaces where there are multiple actors, a user may want to know why their Uber ride was not approved or turned down, right? Or same thing, as you said, the driver may want to know why he's not getting paid more for this trip and what he can do in order to change that. And if recourse is even a good thing in those settings, I think a question that we should also ask before we get there. I think there is a lot of potential and opportunities there. But I think the way the existing literature is, I would say maybe we need to be a little bit more cautious for a few more years before we sort of try to scale this up to marketplaces. But great idea. Thank you.
Okay, let's get a question in from Fei-Fei.
I've been just so intrigued by all the audience questions. Excellent questions. I want to get to differential privacy a little bit. Start with the more technical question, but really thinking about the future and the application, especially queuing the next panel after our keynote is on foundation model and large models. That there's a tension now, right? We've been excited by differential privacy computing for a while, but that complexity and computational cost is really high. In the meantime, modern AI is moving to these huge models driven by huge amount of data. We'll hear more of the foundation models. So on the technical side, Don and Om, how do you see this progress of privacy computing catching up with these large models and segue into the more path to application? Are we going to see practical applications of privacy computing on large models soon, or this is still, more or less only showing up in URIPs and ICML papers?
Sure. So that's a great question that researchers have been constantly working towards improvements. So I personally think of privacy as an enabler. So for example, today I talked about 2 results which by incorporating privacy, we were able to improve what was existing beforehand. So there was a model that was trained on server logs, but when we trained with a private technique, we could train on device. And that actually helped improve utility of the resulting model. With advancements of new techniques, we can even make further improvements on top of that. So there are various areas where privacy can actually help improve the state of the art instead of thinking of it as a trade-off. Like you can get more insights, you can guarantee less memorization, and like overall the utility can be better off with privacy than without.
But there's a cost, right?
There is, like, there are trade-offs in, for example, compute. So if you can design your systems according to those trade-offs, there can be like net gains in other domains.
But the companies are racing off to large models, where they're racing to increase computational resource for these large models, and how does privacy computing come in?
And also, right, and also privacy actually is a really multifaceted concept. And even on the differential privacy side, actually, even if the model is differentially private, it has been shown that it can suffer from other types of privacy attacks and so on. So on one hand, I think, right, it's helpful also for the audience to understand the privacy. Right now, we don't have a silver bullet. Even putting the computation resource aside, actually, privacy is so complex that we don't have a good solution. And then on the other hand, I think certainly, depending on the different types of privacy technologies, yes, the computation resource is always going to be an issue, but then more technologies can help there as well. As Om mentioned, in certain cases, it helps improve the utility, and also there actually has been a growing industry in developing various hardware accelerations for different types of privacy technologies and so on. So for example, I would love to see in the future, like GPUs and TPUs, they have secure enclaves in there, so you can really do secure computing. As you train these large models, essentially you get a certain type of security privacy for free. And then also on the differential privacy side, there's work, including our own exploration also, in terms of how you can get, in certain cases, you can get differential privacy or this kind of privacy guarantees for free. So when you do the training, when you do the training data set in a certain way, that you can get some of these privacy guarantees for
That's
free.
an excellent question for this afternoon's keynote speaker from NVIDIA, privacy hardware. So we'll take a note of that.
And I'm afraid I think we have to wrap up this session now, so sorry for the people whose questions didn't get asked. But if you'd like to follow up with them, if you wanted to email HAI, we can make sure the questions get to the speakers.
I'd like now to welcome Kavita Bala onto stage. Kavita is the Dean of Cornell's M. Bowers College of Computing and Information Science, which houses the departments of computer science, information science, and statistics and data science. Kavita received her master and PhD degree from MIT and her bachelor degree from IIT Bombay. She was a postdoc researcher at the Program of Computer Graphics. Kavita co-founded GrokStyle, a visual recognition AI company, which drew IKEA as a client and was acquired by Facebook in 2019. Before becoming dean, Kavita served as the chair of the computer science department at Cornell. Welcome, Kavita.
Thank you. Thank you, Fei-Fei, and thank you for being here. It's a pleasure to have this opportunity to talk to you. Today I'm going to talk about work in my group that I've been working on for a couple of decades now, but primarily this last few years is what I'm going to focus on visual appearance and understanding, starting all the way at micron resolution to planet scale and world scale. So before I start, I'm just going to give you sort of an inspirational example. I don't endorse this particular movie but necessarily, but this movie, Anon, had a very interesting visual interface of how a protagonist was interacting with the world. So as this person walked around, the real world had overlays of visual information that was interesting to him. He happened to be a car aficionado, so it showed him information about this particular car he's seeing, so that as he walks around, he gets enriched from the experience of seeing things in the real world. And to be able to tell you what a car is just by a photograph of it, you need the field of computer vision's visual understanding research to drive that kind of technology. He walks further towards the back, and actually, as you get closer to these models, you realize they're not real models, even though they look very realistic. So their appearance is such that he's been showing different things that he might want to purchase. And to do that in a good way, you'd need research on realistic appearance. And then in a completely new, reimagined universe of window shopping, as he walks up to a window down the street, he sees all of these items. His technology, his interface gives him all the information of what he's seeing, and he can just hold it right up and decide right then and there, without touching anything in the real world, whether he wants to buy it. So I show this, and to achieve this, you need a real-world photograph. You need to be able to do what is called inverse graphics, is figure out all the material shape properties of this object, so that then you can imagine it virtually, and he can interact with it. So I show these examples to give you an illustration of the kinds of technologies we are now building. You're hearing a lot about augmented reality, mixed reality worlds. These are the kinds of technologies that drive it. Now, there are many questions that come up if we were to live in this world. That movie particularly looks at, for example, the security aspects of it, which was discussed at length this morning. I'm going to focus on the visual technologies that drive it, which has been the body of research that I have worked on. So in the area of research where you start off with a virtual model and make it look so real that you can't tell the difference between real and virtual, that's the field of computer graphics, rendering in computer graphics, actually, in the area of realistic appearance. And conversely, there's the other direction. You take a photograph of something and you understand what it is. So you understand all of its properties, but then you can build on that understanding to understand maybe bigger properties of the scene and the world around you. So in today's talk, I'm going to talk about 3 areas of research that are just depicted here. Physics-based visual appearance models, so models that really capture and accurately the physics of the world of objects interacting with light. Inverse graphics, as I said, building models of the world. And then at a very large scale, taking all of these technologies that we have and trying to do visual discovery, so using visual recognition, but at world scale to understand our world around us. And the first 2 are pretty different from the second, so there'll be a pretty big logical break in the thinking in the talk, but I hope you'll bear with me. All right, so let's start off with physics-based graphics. In 1988, this is the famous Cornell box that introduced what was basically a visual Turing test. One of these is a photograph of a real box, and one of this was a rendering at that time of a virtual rendering of a virtual scene. And the concept that was introduced is we shouldn't be able to distinguish between these 2. And just for your edification, real on the left, virtual on the right. This has spurred decades of research as people have tried to meet this goal of the virtual Turing test of not being able to distinguish virtual from real. Of course, the world is not made of materials as simple as this. In the real world, there's a lot more complexity. So we have fabrics shown here, as you saw in that model there, skin, rocks, and other trees, leaves, all of this stuff, food, and all kinds of biological matter in the real world. And you're continuously interacting with this world, and you're making judgments about what you're seeing and whether they look realistic. So dealing with this complex materials has been a big challenge in the field. And as I said, this is one of the big areas of research I've focused on for several years. So I'm going to talk about one set of projects around properly capturing the appearance of fabrics and cloth. And the question that we asked ourselves is, actually, look at these 2 pictures. On the left, you see velvet. You as a human being can immediately recognize that. On the right is some sort of a shiny silk-like material. So why can you recognize that instantly? What makes velvet look like velvet, and what makes silk look different from velvet and look like silk? Well, it turns out the answer lies in the structure of these materials. The cloth and fabric are not just surfaces. They actually have structure to them. And if you capture that structure, you capture their essence of their visual appearance. So what we did in this original set of projects is we looked at micro CT scans of these materials. So here's a swatch of velvet and a penny associated with it, just to give you a sense of the scale. And in the middle are the CT scans that we will show slices of. On the right, you'll see the structure of the velvet, which will have this characteristic appearance. Velvet is a very fuzzy material, so there's a substrate and there are yarns that come out of it. And you can see that on the right there in the 3D visualization of the data for velvet. So that's velvet. Conversely, silk is very different. It's very tightly interwoven warp and weft yarns put into a particular pattern. And in fact, because it's so tightly woven, that gives it the classic shiny appearance that silk is very famous for. So what we found, to our surprise, is once you capture the structure with these volumetric models that you get from CT scans, you're actually almost there in getting a complete appearance model for these very complex materials. And just to give you an idea, CT scans nowadays, they're kind of like Kinko's. You can send a sample and $200, and half a day later, you can get all of your data that represents them. So it's a really new modality that's very exciting. Once you have the structure, it turns out a small amount of extra information that shows the optical properties, for example, the color, et cetera, is enough to give you a complete model, so that we were then able to produce the most realistic models to date of these kinds of fabrics. So I'll give you a little flavor of how we use this information, these volume information and the photographs that go with it. So when you have these volumes that come from the CT scan, there's some density to them, and there's sort of an orientation to all of the way the fibers are in those volumes. And if you capture that, essentially you're capturing this arrangement, the structure, so to speak, of these materials. And meanwhile, from the photographs, you're getting the base color, so to speak, the albedo of the material, and some idea of its shininess, the spread of light when it goes through that volume. And together, that gives you that model. I'll show you now examples of this. You can see the volumes on the left and the appearance that you can get. These are the highest accuracy that you can get of these kinds of models to date. Partly, and they capture exactly a very characteristic appearance. The silk looks shiny as it's expected, and the asperity, the velvet has what is called asperity scattering, the very characteristic highlights that you get on the rim of the model. And at that point, this moved us forward quite a bit. Since then, we've done a whole bunch of research on actually generalizing these models, et cetera, so that we can then use them. And what's the ultimate goal? What to use them for what? Might be a good question to ask. And the answer is really that we want to make these kinds of tools available so that designers, industrial designers, textile designers can do digital prototyping such that they can predict the appearance of a real woven fabric. So in an industrial loom, you have actual yarns on spools, and they're fed a weave pattern, and then an industrial loom will produce a fabric like a picture there shown on the right. And sort of in our modern day visual Turing test, we want to create essentially an entirely digital pipeline that achieves the same effect. Using this combination of CT scans and photographs, et cetera, we should be able to produce a virtual rendering that matches reality so that a designer can make important decisions without having to actually build a fabric ever or fabricate the fabric ever, and can make important decisions with fast turnarounds, low trial and error to get to the outcomes they need. So that was sort of one body of work. In fact, we built further on that, and these volume models are pretty heavy and hard to work with. So we actually created lower dimensional models with 22 parameters that are more intuitive, that represent the structure of these materials. And once you have them, you have a lot of power as a designer. Now, I'll just say quickly, there is a challenge here. How you find these parameters is a difficult problem, and that leads to the inverse graphics that I'll talk about shortly. But given these models then, and here you can see two pictures of yarns. On the left of each picture is a photograph of the yarn, and on the right is our virtual fit. It's a complete virtual rendering of that yarn that we have fit to it. And now you have textile designers have a lot of power. They can take these yarns, and without actually manufacturing a completely different kind of a yarn, they can go and they can look at what would happen if I produced a new kind of a physical yarn that had a different twist parameter. How would that look? And if I like how that looks, maybe that's the direction I should go. And you can do this all without any physical trial and error if you have good predictive models to produce appearance. So I wanted to just motivate this area of research on physics-based visual appearance models, because we'll come to how does that fit with learning very shortly. But digital prototyping and industrial design, all of the techniques, all of the areas that really rely on this kind of virtual techniques has a big financial impact on them. They need these kinds of predictive models so that they know what they're getting and they can rely on it to make important decisions that change the outcome of how their design process operates. So the next area I'm going to talk about is the area of inverse graphics. So let's say we have all of these models. The question is, how do you actually fit to those models, so to speak? And that's been a big area of research in computer graphics for a long time. It's recently received a lot of interest because of the possibility of adding learning to it, which has enabled new kinds of capabilities in this space. So here's what you're trying to do. If I go to that watch example, you're taking a photograph of something in the real world and trying to create a fully virtual representation of a shape, its material, and maybe even the lighting that contributed to its appearance so that you understand what you're seeing. Before I get into sort of how we actually would go that, I just want to go into that area. I just want to give you a sense of why it's difficult. So materials like metals, for example, when light hits them, light bounces off them, and they're still difficult to simulate because you have to capture light bouncing around a room like this, hitting all the surfaces in the scene. That's a big problem of global illumination. But there are other materials, skin, food, and all of the things that actually a big part of the world that we're living in right now, have this extra complexity that light doesn't just bounce off the surface, it goes in and interacts with the surface. It's called subsurface scattering. It scatters within the material, and that fundamentally changes the appearance of these materials. And you really want to capture that correctly, but it's quite complex to simulate and represent. And just so you know, you use judgments on subsurface scattering all the time. If you look at a piece of sushi and you're deciding, do I really want to eat this? You're making a judgment on its freshness entirely based on how that appearance is coming and presenting itself to you. So I'll give a hint, just a flavor of different techniques that we're trying. This is a very exciting area right now with a lot of interest in it, partly because of the development of a new area of research with great researchers across the community working on differentiable graphics. And I'll talk briefly about that. But let's say we want to solve the problem of inverse graphics. The problem we're trying to solve is really take a picture of something. Can I figure out what the material properties are of this object I'm seeing? Right? In an ideal universe, you'll have some sort of a learned representation there. So you take the picture and you can spit out the material parameters. In this case, those three correspond to various scattering parameters. How far does light travel in a medium? How much does it spread out when it scatters? What's the albedo of the material, et cetera. So I want to create this kind of a pipeline, and the reason there's promise to do that now is we have physically based renderers that are simulating the entire physics of light that work pretty well. So you can imagine combining them with a learned representation, and if you have this end-to-end pipeline, then if you match that output image and that input image, and you get them to match, your loss is minimized, then you're able to hopefully recover the material properties that are sitting there in that middle of the slide. And to do that effectively, you're effectively combining learning and physics, and you're inverting sort of the physical rendering process in the world and trying to come up with the inverse parameters. This is a very exciting space. As I said, recovering shapes and materials is hard. I will say to make it work, you need that rendering engine R to be differentiable, and a lot of recent research has focused on that. So I'll now give you just a flavor of some of the techniques that are out there that use this. If you have a differentiable renderer, then, for example, you can take lots of photographs of the object, this particular fish, for example, and you can have different representations for the shape, material, and lighting and recover them using this combination of learning and physics in this pipeline. So you can represent shape with sign distance functions in this case, the materials with diffuse and specular representations that are learned, and the lighting with spherical harmonics, spherical Gaussian, and you put that together and you have an end-to-end representation for simple objects. Once you have this, you can then relight the object. So just like the guy was holding up his watch and was able to see it, you can potentially try out different settings, try out different metals that you want to make of that material or different materials of this fish and see how it would look. So you get that power of design, intuitive design, through these kinds of mechanisms. To make this work, and I'll just give a brief hint of the kinds of problems you deal with. As I said, we're one of many researchers who are really pushing the state of the art in this space right now. You need to have a differentiable rendering pipeline, and what I mean by that is you need to be able to differentiate your loss with respect to the whatever properties you're recovering. So for example, in the case of material properties, you need to differentiate with respect to that. And I won't get into the details here, but here's an example where we're recovering material and geometry, and the details are in the paper, but we're able to actually characterize this differentiable, the differentiable rendering aspect using the chain rule, and are able to compute it just using some simple sampling on the boundary of the surface. And that gives us the information we need. Now we can build a pipeline like this one, let me see here, where you have a cell phone camera, you can take a few images of an object and just walk around it very easily and create, starting with the coarse initialization, this extremely fine detailed model just with a cell phone and at-home equipment, essentially. And here are examples of now taking those kinds of models and then applying it in completely different settings, augmented reality, virtual reality apps, et cetera. So that's all been looking at the problem of surface-based models. We were very inspired by looking, I told you subsurface scattering is a very important phenomenon in in the world because of the skin and the food and all of the things that we have. How could we capture that? So before I get you too excited, this is actually a photograph of real food created by an artist, and I give them a lot of credit, and served as an inspiration for us for this project. So these are it's called cubes, and they carefully, meticulously created 2.5 centimeter cubed cubes of 98 different food items. And just to give you a sense of the complexity of the world we live in, these are each of the beautiful cubes. They aligned it together, put it in a line, and took a photograph of it. So this is not rendered, but we were inspired by this to try to create models of this kind of complexity of food. And as I said, the thing to remember is because they have very complex subsurface structure, you have to capture the appearance of that. So to appear, it's going to appear at SIGGRAPH this year. We looked at, again, the differentiable rendering, and this one is quite involved, so I'll wait for you can read it in the paper when we release it shortly. But we actually developed a whole differentiable rendering pipeline with subsurface scattering as the core material property that we are recovering. And once you do that, again, you have a pipeline where you can take some photographs of this object, and we've created these renderings of kiwi and dragon fruit for the first time. There's still a long way to go. The quality isn't quite there. You can tell that this is a virtual model, but it starts to get the essence of what these materials are. So all of this begs the question, why are we doing all of this detailed modeling when you can just use large data and learn this, right? That's a question, and we're seeing amazing work coming out. For example, DALL-E 2 the paper was just recently released, and it's amazing the kinds of things that they can do with a language-based model to edit the world and to change it so that you can visualize the kinds of appearance you can get, both in a stylistic manner, as you see on the top, but in a realistic manner if you see down, right? How do you get that? So what is the relation between these two? So I'll tell you, this is sort of based on just a couple of decades in this business. I think combining learning and physics is really exciting, and we are at that time when we think we can do that. And the reason you do want the physics, though, is because of this need to do predictive rendering. So here's an architectural visualization of a scene that you would like to visualize before you actually build the scene so that you understand how it looks. And I'll give you sort of the motivations to summarize all the arguments I've made up till now is, when we were looking at the fabrics, we didn't even understand why they looked the way they did. So understanding the visual phenomena through the physics is actually an important part of how we can explain why velvet looks like velvet and it's different from silk. But then additionally, the key goal here is not only to produce something plausible, though that's an important goal in its own right. There are many creative tools that can produce plausible output, like you can see with DALL-E. And that is a very exciting domain for lots of people to explore and for citizen artists to design. But a lot of our work that we do sits actually on the predictive side, where we want to correctly predict how appearance will look before we build an item or build a building that's hundreds of millions of dollars. We really do want to make sure we've simulated it properly to understand how it might play out. And that brings to an interesting problem that actually we identified in our field. It used to be the case that we were told artists really just want artistic control and they don't care about the physics. That was the belief till the 90s, when we finally figured out how to get the physics to work properly so that you can use it in tools. And then it turns out artists actually love having the physics. And the reason is because artists want control on the artistic process. They don't actually want to waste their time simulating physics, which they hope nature gives for free for them. So once you realize that, what you really arrive at this place is you want to have this combination of control along with physics and designing tools that have that, not just a black box that's learned, but one that has the physics in it and can combine the two of them. That's, I think, where there's a lot of interesting work to do. So we don't know yet how to do it in our community, and there's a lot of it's just being developed as we go, but I'm excited to see what the next 2 years bring along that space. All right. So I've talked about the first two parts of the talk. I'm now going to spend, as I said, switch gears pretty substantially and go in a different direction, which is looking at this question of if you have all of these images and you can understand what's in them, what can I do with that knowledge? And I'll talk briefly about a world-scale visual discovery, which is an area of research we're working on in this space. So remember the time when that guy walked down the street and he looked at these watches and his interface told him exactly what he's seeing. That problem is called fine-grained object recognition. It's a big area of research in computer vision, and it shows up in many places, not only in product recognition, but also, for example, chandeliers in real estate, for example, in this indoor house scene, or understanding whether an influencer is carrying a particular item of fashion. All of these require you to look at it and say, this person is carrying X. And it's not X like X is a handbag. That all of us can do. It's X as in here's a particular brand of handbag, which most of us can't do. At least I can't. I don't have that level of knowledge at all. So essentially, we have the promise of providing expert level, and maybe even more than just any one expert level of knowledge through visual recognition. And that's a very exciting space to be in. So we worked on some of the space with my student Sean Bell. We actually worked on fine-grained object recognition, where we would recognize an item like this and say this is not only a fire pit, which I don't know if you would have recognized just by looking at it, but it is this particular kind of fire pit and where you could get it and who the artist is who's created it. And as Fei-Fei mentioned, we rolled this out with IKEA in their augmented reality app. So this is where all of those earlier visions of that interface are starting to become true, where we'll have visual recognition and we'll have virtual renderings all intermixed together in augmented reality apps. That's our hope. The work that we did here is actually now part of Meta's shopping AI, GrokNet, and their tagline is to make every image shoppable. So the work is having an impact now, but separately in my group, we've been looking at a variation on that problem, not to make every image shoppable per se, but to make every image understandable. So what do I mean by that? So first, before I do that, let me just, of course, you all know this, that's why you're here at this conference. But we are, of course, collecting information at an unprecedented scale at this time, visual information, whether it's photographs or videos, and now satellite images. So it used to be that we had about 50-odd satellite images a couple of decades ago. There are 1,500 now, and they're uploading 100 terabytes of data per day. And in fact, that's a direction I'm very excited about, understanding images at satellite scale so that we can understand how our world is changing and see what's going on across the world. So we want to gain, and if all of these images, it sure seems like we should be able to understand more than what any one human being can understand with their ideas or their worldview. And so the hope is, can we gain insight at planet scale by looking at all of these images? So we started working on this field, and the field is very broad. I'll talk about one slice of work that we've been working in this space, but the idea of doing world-scale visual discovery and understanding. So we can ask questions like, how do we live? What do we wear? What do we eat? And how do things change over time? How is the planet changing over time? I will say that in this work, and done with Utkarsh, Kevin, Noah, Bharat, we started to work actually particularly with cultural anthropologists and with sociologists, because they are fascinated by these kinds of questions, except they don't have the tools to really explore them. So when you think about what a cultural anthropologist or a sociologist does in their field studies, they'll go to some locale of the world where they have a hypothesis of what's going on in that place. They do a bunch of interviews, and then they try to then understand, build up a theory or build up a cultural understanding of that space. And so when we reached out to them, they were incredibly excited to have a tool that they can use to maybe expose the kinds of questions that they could ask, that they would then follow up with very rigorous field work. They weren't planning to ever give that up. That's an important part of informing these outcomes. But it'll help them actually reach, seed hypotheses as they go along. So the particular one we worked with, a cultural anthropologist who was very interested in understanding how clothing changes across the world. And actually, this relates to something I was very intrigued, something Liz said in the earlier panel today. So why do people dress differently in different parts of the world? Well, it turns out weather plays a big role. Most of you are wearing clothes that you don't normally wear in summer here because it's a little chillier here than it is normally in California. The activity or the occasion demands a certain kind of clothing, whether it's you're going to a party or you're going to a sporting event. Culture changes certainly what you wear. Different parts of the world dress very differently. And of course, there's fashion trends. There's actually fashion influencers, et cetera, who change what you decide to wear, and that plays a role. So we decided to study all of this within the context of these projects, where we got a set of images for about 8 million images of people from different parts of the world. And we developed a simple recognition algorithm to recognize what clothing they wear. So it's just simple 12 attributes. But we wanted to understand what can we glean from this very simple analysis. And the main point is, let's assume recognition works. What further insight can I get about the world that I live in? So we looked at, if you look at the classifier and then you just look at the embedding of the images that you get using that simple mechanism, you can start seeing some structure in the clothing that we've analyzed through this process. And I'm assuming the projector is not washed out, but you can see on the top right, there's sort of greenish kind of clothing, and the bottom left, there's a reddish kind of clothing. So there seems to be some structure to what we've learned of the clothing that goes across the world. And in fact, we characterize these using a mechanism just to seed some number of style clusters and try to understand what these style clusters are. So we show here sort of these top 4 style clusters that we get out of this simple analysis. And they show interesting things. So for starters, you can see each cluster actually shows a very distinctive type of clothing. But more importantly, we can actually start to understand where the data comes from. And you can look at the cities on the x-axis and the time of the year that you're collecting on the y-axis. And now you start actually seeing a lot of structure. For example, this very distinctive top row is called all the women there are wearing, most of the women there, there's some noise in the data, are wearing this distinctive headgear called the gele, and that comes from Lagos. Here in the middle 2 rows, you see the hijab, which is worn extensively in Cairo and Jakarta. Other places of the world too, but those particularly plays a heavy presence. And down here is something that's kind of ubiquitous across the world. It's sort of cold weather. You're seeing essentially winter in the northern hemisphere and also the southern hemisphere at the other months. And you're seeing people dressing up for cold weather across the world. So just by analyzing the data, we started to understand a little bit about different unique aspects of culture in different parts of the world. And so that led us to the next set of next project that we did in the space, is trying to understand how things change over time. Can we detect temporal trends and events by analyzing this data? Again, we take these recognition, and then we actually fit simple curves to understand whether there are weather-related behaviors shown here in the red, or there's something more exciting going on beyond just weather. So here's an analysis of some of the data we get, and if I look, I think at the middle one, you see, I think that's Delhi, and you see, sure enough, in winter, people wear more layers, and in summer, they tend to be more lightly dressed. That makes sense, so that forms our baseline. But then what's interesting is out pops from this very rich data automatically events that don't match what you'd expect to happen in a particular place just based on predictions of weather. So now we start to find outlier events like this one. So this is Chicago and people wearing green, and there are spikes at one specific time of the year every year in March. And what is it? It turns out, for those of you who know, people are nodding, it's St. Patrick's Day over in Chicago. Everybody wears green. It's a very important cultural event. So we have fully automatically found something that is very important to people in Chicago that you might not know if you're not a native of Chicago. We found another very interesting example. We actually didn't know about this at all, but out of the data popped this political rally that was called Catalan Way, where everybody wore yellow shirts and formed actually a human chain. This was to protest. This was over in Spain. And again, the data just informed us about a cultural and political event that we were completely unaware of, and that we learned about the importance of an event to the local population. In fact, going further, we did all kinds of analysis about worldwide cultural events. So we can see the Stanley Cup, we can see various sporting events that pop up, for example, the Melbourne Cup over here in Australia. We identify something that most of you probably know is important, but the data just pops it right out. Fashion Week in Paris pops out here. New Year's is important in certain parts of the world. Father's Day is important in certain parts of the world. All of this just gets exposed, and we as we were computer scientists, but working with the cultural anthropologists, felt we were learning about the world through understanding these cultural variety that exists in the world around us. For those of you who know, in Calcutta, Durga Puja pops out, which makes total sense for those who are local and is probably completely alien to people who don't know what it is. So it's a wonderful way to learn about the world around us. So with that, I know we have to get to the end. So I just want to wrap up and just talk about these very two different worlds, but we live in an exciting time where we can bring learning, large data, and physics together to create sort of these new kinds of interfaces with the visual world that didn't exist before. So I've talked about these 3 projects that we worked on in my group, but I'm really excited, as I said, going forward, looking at very large-scale visual discovery, learning visual understanding, and going all the way from micron resolution understanding or what makes things look the way they do, to planet scale, satellite scale. How is the world changing, and well, what are we doing to help it? So we live at I tell my students, this is the best time to be doing research in this space. We're making science fiction a reality. But of course, with great power comes great responsibility. And that's one of the goals of this forum, is to work with a very broad range of disciplinary experts to understand how AI can be used to improve our understanding of the planet, culture, and more. All right, thank you. And thank you. And
you can have a seat.
Thanks.
In the middle.
And I should say, I do want to thank all my wonderful collaborators. The green are the students who did all the work. They're not students anymore, but they were. And the blue are my long-term collaborators. And with that, I think we can go.
Thank you, Kavita. We have a few minutes for questions. Audience, as usual, there are microphones on the aisles, and I'll be moderating these questions. All right. Well, I'm just going to start by thank you. That was such a fascinating talk. I work in computer vision, and Kavita, you're one of the few people whose research has really traversed both computer vision and computer graphics. That was just fascinating. If we're not having audience questions yet, I want to start with a couple of questions to. There's a lot of technical questions I want to ask, but let's just broaden up, because for someone like you who's being a leader, technologist leader in the field of computer vision, computer graphics, and now a leader in higher education, I think there's a lot of things I want to explore in this very short amount of time, and waiting for audience to chime in. Let me start with something that was already mentioned in the previous panel. It's the issue of bias. You work a lot with physical world, materials, objects. Is there a sense that as long as we're dealing with physical world, we're not worried about bias? Because what kind of bias is there in materials?
Oh, that's a good question. I must admit that bias is not so explicit in that context, but there is an implicit one. So and I didn't talk about that work today, but we had this project on materials in the wild, and we were trying to understand materials in different parts of the world. And of course, it turns out that in richer countries, there are richer materials. And so, in fact, if you only restrict yourself to the kinds of pictures that you get, and initially we were looking at real estate pictures within the US, you form a very different model of the world and the materials that people use. There are mud huts with mud stoves that are, and once you expand to actually include images that include India, Africa, all of those countries that have a very different profile in how they approach, in fact, the material world, you actually expand the kinds of materials you recognize and the kinds that you should develop representations for. So we were actually, we had done this work 6-7 years ago when the idea of bias was just starting to ramp up and the recognition of that. And we also felt that, yes, we were seeing this very clearly. Real world life is very different in different parts of the world. The clothes they wear, the kinds of materials you use, and depicting them correctly and accurately requires that understanding of the bias and how to undo that and really have a broader understanding.
And how do you convince your students that they should care?
I was fortunate to have students who did care, perhaps. So but there's a bigger question, actually. That's a great point about just generally in education, in the domain that we are in universities. You do need to make students care. And I will say, so I'm at Cornell, and we have this computing and information science. As Fei-Fei mentioned, we have 3 different departments. And early on, this is 20 years ago, we actually created a very interdisciplinary department that had people with computer science, many of them degrees, but worked with sociologists, science and technology studies, the law school, et cetera, and very interdisciplinary department. And if you don't do that, and at that time, people just thought technology is technology. We'll toss it over the transom and somebody else will deal with the societal implications. This decade has proven that is completely wrong, and venues like this are starting to take it head on. How do we address this? Companies are also, to a certain extent, they have different motivations, are also tackling it. But we need to bring it to the education, into all the courses we teach. So we teach now an ethics course at Cornell. I know Stanford has an exciting one. What we found is our students did not have the language to even understand how to grapple with the ethical questions that they were going to have to do as they're writing their software in whatever job they were doing. So we feel it's important not to give them answers because we don't know the answers, but to give them the language to ask the right questions so that when they're grappling with them, they're at least able to know how to look at the question and maybe where they should go to get help. So that's one piece. I think we have to change fundamentally education in the computing and information technology world to hand in hand understand societal implications in all the technology that we're doing.
Thank you. That's music to my ears, and thank you for leading that at Cornell. It's so important. We do have an audience question. Let's introduce yourself and be brief with the question.
Yes, my name's Neelam Ram. I'm in the Communication and Psychology Department here at Stanford. Thank you very much for the very inspiring and fast-moving talk. I'm curious about how is it that you disaggregate the context of the specific object which you are looking at. So you had some variables that you brought in, such as geographic location or the temporal trends. Is there a way that we can identify the scale at which we should be looking for these context variables, the background lighting, the room, et cetera? And what happens if we get it wrong?
Well, I think we have to be very cognizant, and this is actually how do you avoid getting it wrong. I'll say we always work with domain experts to help us to stay honest. I think so I'll answer that second question first. But it is valuable to think about the context, but you have to balance that also with the privacy of the amount of information you're extracting from a photograph somebody chose to share. So I'll say in the work that we do, we don't use the person's information at all, right? We only look at, for example, in that particular project, the clothing that they have. And all of us know, at least all of us have Zoom backgrounds where we actively, the reason we include a Zoom background is because we don't want to reveal anything about our context to the rest of the people who are there. So there is a rich source of information there. We have to be careful about how we include that. I'll say in all of these deductions you make, when in this case we are trying to understand cultural differences across the world and how people dress, if you have a person from that who's an expert, they inform you about, well, this thing that you think is an effect is not an effect. It's actually bias in the data because that country, and a perfect example is young people post pictures of themselves and old people don't post as many pictures of themselves, right? The whole selfie thing is more a generational thing of a particular kind of generation. So you miss an entire quantity of data for a particular slice of the population. If you have an expert in the field, they help you with that and they help you find the right resources to augment for that.
That's a great question.
Just one another quick follow-up is, when you embed the physics model inside of the learning process, the pipeline,
yeah.
How important is it that that becomes interpretable? Or is it okay if we put the wrong physics model inside, and what are the consequences?
I'm a physics diehard, so you should never put the wrong physics model in. Physics is what nature gave us, and you should put the right model. But the whole point of that is that we want interpretable knobs, right? And in that case, those interpretable knobs are the material properties of the object that you're recovering. There are other kinds of knobs. So in the graphics community, there's a lot of interest over time has been around perceptual knobs. So you don't necessarily change the actual material properties. You change something that affects your percept of the material. Is it shiny or is it not? So would we get those knobs? That would be fine too. But the interpretability of it is all pretty critical for that. Otherwise, you're just monkeying around with random knobs and don't know where you land. Now that I have a very specific worldview on that, as you probably realized, and I know it'll be good to talk to more people who have a different worldview.
Physics is what nature gives us. We shouldn't waste this. Okay, so you mentioned something really fascinating, visual Turing test. And you showed this very cute example of Cornell box. That was what, 80s, 90s?
88. 80s, yeah, and it's still there in a...
Fast forward almost 4 decades, 3.5 decades, we've gone from Cornell box to a deep fake video of Zelensky surrendering in the war. Comment on that. And especially as an educator.
Yeah, again, this is, with great power comes great responsibility. This is a power we have now unleashed, and we have to think about how to use it responsibly. So when I think about the kinds of we will need to develop technologies to be able to tell when images are doctored. And this has been a problem that has existed for a long time. In fact, Stalin famously, since we're talking about Russia and Ukraine, Stalin famously would do a lot with image doctoring in those days. We weren't just that easily fooled. So there are multiple pieces to it. We need to educate our audience, for starters. We need to educate, of course, our students, but we need to educate the world, actually, to recognize I don't just believe everything I see. In the old days, would you believe, would you trust your lying eyes, right? That was the axiom. That's not what we can use right now. We have to say, you can't trust your lying eyes. It's possible that somebody doctored this image. So we need to develop technologies to really be able to detect that. And there is a lot of work. I know that this has been ramping up in different companies. So once we have those technologies, once we have a more educated populace about the dangers of that, you will still have a whole bunch of people who want to believe what they want to believe. That is actually a reality of our time too. There's a longer education process related to making people understand that it is important that there is this idea of trying to get to a common, sharing across differences, rather than just sitting in your corner believing what you want to believe.
Thank you. That's so important. I mentioned earlier, Kavita, that you are one of our nation's higher education leaders in computing as a dean of Cornell's, a very important school. I want to talk about this because you also have a unique view, having collaborated with the industry. In the world of computing, and of course driven by AI to a large extent, there's a huge just gravitational pull to industry, our talents, the computational resource, the data that's available. What is the role of higher education in this moment where there's tension?
So again, I have a strong view. We are here to keep...
We want your strong view.
We are here to keep everybody honest. That's what you can do in a university, that at the end of the day, as long as you are reporting to somebody with a financial obligation to that person, as a lot of companies with the best of good intentions, they have a very different objective function they're optimizing for. Universities aim to, pursue the truth and do it, without bias. And we are here to help, and we have to work with these. I will say, though, I do worry, right? We get starved out of resources, whether it's compute resources. We don't have access to the large scale of data that's available. We have to think about ways in which that kind of, or approximations of that, are available across the board to the universities and to the academic communities so that we can help with the research. Now, it's a very difficult time we're in, and I hope that we can maintain that strong voice while we work with, and I know there are many industrial partners here who will reach out to the academic partners so that we can actually partner together to keep the world honest.
Keep us honest. That's a great message. We've got one chance for audience question, and then we have to wrap up.
Thank you so much for the talk. I was on the edge of my seat wishing I was in grad school again. That was really a lot of fun. As you've been incorporating models of reality into a variety of machine learning contexts, I think there's a lot of lessons that you could potentially learn. So large language models, for example, just run happily over large amounts of data, but are often unconstrained by reality. As you've been putting these models, embedding them in, there's lessons you might be learning like computational costs, because if you really want a perfectly high fidelity physics model, I mean, you need to go quantum, I mean, you need to go crazy, and that's just way too computationally expensive. So when you're making those decisions about what models of reality include, there's constraints that you have to deal with, as well as understanding how to make these two worlds work together. I was just wondering if you could just like comment on like lessons learned that would be relevant to this audience.
That's a great point and a great question. And I'll say in the computer graphics world, you know, we started off with these simple boxes of painted materials, and we have got into an incredibly complex, the kinds of materials I was talking about. But that's not actually the end. You're exactly right. There are people who are modeling diffraction and wave phenomena, and that's actually a big part. If you actually pull out, any one of you pull out your phone and you look at the phone at the right angle, you'll actually see the kind of diffraction phenomena that have to be modeled if you want to get the appearance correct. So what we have found is there's actually an endless, at every stage in computer graphics, people have said, we don't need that complex physics stuff. We can just, we'll be fine. And then somebody goes and figures out how to do it well, and everybody goes, well, obviously, we always needed that stuff, right? That's happened so many times in my career. It's almost, so when somebody tells me, we don't really need that level of correctness, I go, you know, once we figure out how to do it efficiently, I bet you'll show back and tell me, come back and tell me you did need it. So we keep learning, we keep pushing, and, you know, this, in our case, we have physics that, you know, gives us there's a ground truth there that you can aspire to. There is you have to look at it for the tasks. For example, these large language-based models, I think, could be incredibly valuable for creating, you know, creative output from random citizen artists, as I said. But they're not the people who are going to be doing the kind of predictive stuff that you need when you're actually building things with financial impact on them. So you pick the right model based on the task, and ideally what you have, and that's the whole question, can you get one general model like our brain is-ish, and can you then optimize it? But I would actually argue there are different experts here, and we also don't have like the one model. I'm not an expert on a whole bunch of topics. So you will have to have that specialization based on the needs of the task and go as far as you need to go for the task that you need.
Kavita, thank you so much.
Thank you.
It's such a pleasure.
Thank you.